Unit 5 is all about chemical thermodynamics. And chemical thermodynamics all have to do with heat. Okay? So we're going to start off this unit talking a little bit about heat and how it affects things like kinetic energy, things like that. So when you increase the temperature of particles, those particles have a greater kinetic energy. In physics, the kinetic energy equation that they use looks like this, okay, where they say KE, kinetic energy, is equal to 1/2 times the mass times the velocity squared, okay? So when you raise the temperature, what you're actually raising is you're raising the velocity of those particles, which thereby increases the kinetic energy. Okay, if we draw the arrows that represent the direction and the speed or the velocity of the particles, notice that at the higher temperature, the arrows are longer, okay, and that means that they're moving at a faster rate. They're moving in random directions, but clearly compared to the arrows over here, the longer the arrow, the faster they're moving. Notice that all of the arrows are not the same length, though, which means that they're all going to be pretty close to each other, but still you're going to have some that have a little bit more energy than others, so they're not going to be at the exact same temperature. Okay, so for 500 milliliters of water at a temperature of 25 degrees Celsius has less energy than the same volume, 500 milliliters, at 35 degrees Celsius. When you double the Kelvin temperature, that doubles the kinetic energy, but not the Celsius temperature. Okay, again, this equation is given on the AP test. I've never seen a question where you actually have to solve kinetic energy, though. Okay, but as the Kelvin temperature approaches 0, so as it goes down and down and down, obviously the average kinetic energy of the particles also goes down until it also approaches 0. And this can be seen again, similar to the graphs we saw in Unit 4, by a Maxwell-Boltzmann distribution, where you've got a higher temperature. The red line, the purple or the blue line is the lower temperature. And you've got, again, energy of particles. So you've got the average energy of the particles is higher than for the low temperature. And you can see that simply by looking at the graph. Along with samples of different gases at the same temperature, you should also be able to use a Maxwell-Boltzmann distribution for samples of different gases at the same temperature and apply activation energy concept. So let's look at a couple of examples of that. So example 1, it says, on the curve above, draw a curve for particles at a higher temperature and at a lower temperature and identify each. And then it says, draw an activation line barrier going up after the S in particles on the x-axis. Then explain why reactions occur faster at higher temperatures. So at a higher temperature, you might see something like, something even flatter. Maybe something like that. Again, doesn't have to be perfect. That's actually terrible, but whatever. Okay, and at even a lower temperature, you might see something like even higher, like that, and then slowly over. Okay? And then it says, draw a line that represents the activation energy barrier line. So I did that. Okay. So now we can see, so here's our even lower temp. Here's our even higher temp. Okay. We can see that, again, anything to the right of this line, so anything from here over, has enough energy to overcome the activation energy barrier. Notice at the lowest temperature, very few particles have enough energy to overcome the activation energy barrier. Okay, and then at the low temp, again, we've got more, but still not very many. At the high temperature, we've got, again, about that many. And then at the higher temperature, that probably should have gone up a little bit higher. Sorry about that. Okay, again, I just didn't draw it quite right. At the higher temperature, you should have the greatest percentage of particles that have enough energy to overcome that activation energy barrier. So why do reactions occur faster at higher temperatures? Because more particles, this is really important, not all particles, more particles have enough energy to overcome the activation energy barrier. Okay. Now, when two systems that are at different temperatures come into contact with each other, they come to thermal contact, so one's hot, one's cold, the energy transfers from the hot thing to the cold thing until those temperatures are the same. And once those temperatures are the same, we know that that is directly related to the kinetic energy, and so their kinetic energies are also the same. This transfer of energy from the hot thing to the cold thing is, again, what we call heat or heat transfer. Okay, on a hot day when you go outside, yes, of course, it's hot outside, but the reason that you feel that it's hot is because the heat from the hot air particles is hitting your skin, transferring the heat to your skin, and you go, oh, it's hot. Okay, so heat is not a substance. It is simply a transfer of energy from one thing to something else. Okay, and then again, when two things are at the same temperature, you have reached thermal equilibrium, etc. Okay, so let's look at a couple of examples here of this. It says the plot below shows the distribution of particle speeds for equimolar amounts of nitrogen and unknown element Z at the same temperature. So notice that element Z, its peak is a little bit flatter, and again, its peak is a little bit farther to the right than nitrogen's is. Okay, so if the peak is farther to the right, it either means that it's nitrogen at a higher temperature, or it could also be a different element where the particles are traveling faster. Okay, and we've learned that the lower the molar mass, the faster particles travel. So notice the question here, based on the data in the plot, is the molar mass of N2 greater than, less than, or equal to the molar mass of Z? Justify your answer. So N2 is going to have a greater molar mass. And again, because the kinetic molecular theory tells us that the smaller the molar mass, the faster the particles move. And again, notice we've got speed here, not necessarily energy. So with speed there, absolutely, even though it looks like a Maxwell-Boltzmann distribution, this is really just showing you that the lower the molar mass, the greater the speed is. Okay, and then here we can just a summary of that answer. Okay, and then example 3 says the solid curve below shows the distribution of molecular speeds for a sample of gaseous VbO2, whatever that is, at 110. The student incorrectly sketches the dashed line to show the distribution of particles when the temperature decreases to 80. Okay, explain the student's error. Well, here's my error. I put the period before the degree sign. Sorry about that. Okay, explain the student's error. So what happens here is, oh, well, in this case, doesn't it, the way that the student drew this, it just looks like, the speed is distributed the same. It just looks like there's less molecules in there that now. Is that what happens when you lower the temperature of a gas? Do you lose some of that gas? Of course not. Okay, so we know that the correct way to represent that would be to draw, again, a sharper peak that goes taller and then comes down similar to that. Okay, so explain the student's error. Again, lots of different ways you could say that, but I would say something to the effect of the student's peak, the student's curve or whatever, should be farther to the left and taller, and that would represent that you've got more molecules at a lower average speed.